The quiz will be on week 15.
Oh, so we have one quiz and one more test?
All right, let us continue.
Two more tests. One test and one final.
So we had, all right, let's settle down. We had our calculations of the magnetic field due to a current carrying wire, right? And also due to point charges. So remember, you have a, let's say, a line that carries a charge, right? A current, sorry. It's carrying a current, so the current is flowing in this direction. And you would like to find the magnetic field at some point, maybe here, right? At some point P. So, well, take a current segment that you want to use to calculate the magnetic field, and let's say take this segment. The direction of motion of that segment is along the current. So this is the direction of motion called ds. Okay? Draw a vector from the current segment to the point P, and that vector will point in this direction. You can call it vector r. Okay? Then the magnetic field, or a small magnetic field due to only this, will be dB equals to mu naught times I over 4 pi, and then ds cross product with r hat, and r hat is the unit vector that points in the direction of r, divided by r squared. You can rewrite this as mu naught I over 4 pi ds. Instead of saying cross r hat, just cross it with r. Take the cross product with r, but r hat is just r divided by the magnitude of r, so you get r cubed on the bottom. So that's just a different force. We use this to calculate the magnetic field due to an infinite wire that is straight. So a long wire that starts at minus infinity, goes to positive infinity. It doesn't curve or anything, it just goes straight. And we found that the magnetic field looks like this. So B for an infinite wire, or a wire, and I mean by wire, long, right, infinite, straight like this. The magnetic field was mu naught I over 2 pi r. So if you're a distance r away from the wire, this is r, you're here, then the magnetic field strength is this. That's the magnetic field. The direction, if the wire is going like this, when you're above, the magnetic field points out of the board, and it loops. And so when you're here, the magnetic field points into the board. So you can draw the magnetic field so it looks like this. Out. This symbol stands for out, right? You're looking at the tip of the arrow towards you. And then at the bottom, here's N. I would only draw a field. Obviously, there is magnetic field everywhere here. I only drew along this, right? And there is magnetic field above the wire everywhere also. Okay? So the farther you go from the wire, the weaker the magnetic field gets, right? So if you're very far, it drops as 1 over r. So at infinity, how much is it?
0.
0. Just like with anything, pretty much, right? As you go to infinity far away, the whatever it produces, whatever if it's a force, it's a field, it goes to 0, right? That was that. Another way to now figure out the direction of the magnetic field using your right hand. We use our right hand to figure out the direction of the cross product. So let's use our right hand again, not left, right hand, to figure out the direction of the magnetic field due to a current carrying wire. So whenever you see a current, put your thumb in the direction of the current, and then your fingers will curl around it. So you see here at the top, my fingers are coming out towards you, and if I follow the direction of my fingers, they will curl in, and it would be this way. So it goes like this. Okay. So just for practice, let us do one more, or maybe 2 more. Let's say I draw a line, a current carrying wire like this, carries current. going up, it's going upward. So in what direction is the magnetic field at this, here?
Out of the board.
Out of the board here?
And
It would be into, yeah, so put your thumb here, and the magnetic field will be out, and then in. Out. On the other hand, you can also draw the current to be a wire that's coming towards you. So let's say the current now. Maybe I should use a different color. Okay. So let's say the current now is coming towards us. So what does this symbol now stand for? Current coming towards you, right? Not the magnetic field, this is the current now. So in what direction is the magnetic field? Yeah, so put your thumb in the direction of the current, and your fingers would curl, so the magnetic field is circulating counterclockwise. So. So that was a review of what we did last time. Now we would like to calculate the magnetic field due to a current carrying loop. Right? So imagine you have a loop that has a current. The current will not just run through the loop by itself, so it has to be connected to a battery somewhere, and then it drives the current. But for now, let's ignore that. Suppose you have just a current carrying loop. Okay? Somehow there is a current running in. And then the question is, what is the magnetic field on the axis of the loop? Okay, this makes sense. So you have a loop. So, here, current, loop. Right, so let's say you have a loop, and the loop would be carrying a current that goes like this. I'm going to orient the loop this way. Okay? So the loop is like this. I wish I had a loop, but this is the loop. Right? Does that make sense? So that's the loop. So the current on this side will be coming out of the board. It loops around, and then when it gets here, the current is going into the board, right? It's going into the board. And if you like the loop, it's like this, right? This is our loop. It has radius r, let's say. Radius r, okay? And we want to figure out what the magnetic field is on the axis of the loop. Off axis, we can figure out the direction, but the magnitude, it's, I mean, you can set up an integral, you can't do it, you cannot evaluate it exactly. Probably have to do it numerically. So on the axis, we can do it. We can evaluate our magnetic field exactly. So let's say this is the z-axis, right? Z. And we want to figure out what the magnetic field at this point is. The distance z. Okay, so what do you do? Well, we're going back to that law. The Biot-Savary law. So you have the u naught, the I, and the 4 pi. So there is current I, so we got that. And now we need to figure out what this cross product ds and the r hat is to be r squared. Let's figure it out. So I have the magnetic field will be u naught I over 4 pi, and then ds crossed with r hat divided by r squared. That's the starting point. So draw a line from here to here, because that's where the current segment is. That's where we're trying to figure out the magnetic field. So draw a line like this. So let me maybe draw it with blue. So this is vector r, right? I don't draw the vector sign on purpose. Let's just write r. Now, what is the direction? Because I have to figure out ds cross r. So ds is coming out of the board, right? The current is coming out of the board. So ds is in along the z direction. R is in this direction, so what's their cross product? This is probably the hardest part of the problem.
What's the question?
I'll share again.
So the ds is in this direction, right? The current is in the direction of the current. And the question is, what's the cross product of ds and this vector r? Maybe I should draw the vector side.
It's like this one.
Yeah, go ahead. You said
Wouldn't it be like
Uh-huh.
this one?
Like this?
Yeah, like something like that.
Yeah, something like this. I agree. The cross product always produces a vector that's perpendicular to both other vectors, right? So first, this vector occupies one of the axes on the plane of the board. This vector is perpendicular to the board, is out of the board. So the cross product has to be a vector within the board, but perpendicular to both of them. So if it's within the board, it's already perpendicular to this one. Job done. We need to be perpendicular to this one also, and that's how it will point. That cross product will point in this direction. So dB is going to point in that direction. Okay, so how do I know? Again, there is ds, cross it with r. So it makes it hard, but cross it with r, it should be in that direction. All right, so that's that. Now, the claim is, you see this vector b, db? We'll have two components. One of them is along the z, and one of them is horizontal. The horizontal component will cancel. Here's how you can see that. Look at now this segment of current that's going in. So that segment of current that's going in, and let's look at R here now, this R, from this segment. So in what direction is the magnetic field that it produces? Well, you got a segment N, R is this way, so take the cross product, it's N, cross it into this, curl your fingers from N towards this, so it produces a magnetic field in that direction. So the magnetic field, due to this one, will point in this direction. The result is, just because of the angle that's on, the magnet is going to be the same because they're equidistant. And this angle that it makes with the x-axis, this one and this one, they're the same in magnitude, but one is plus and one is minus. So the horizontal component, what happens to it? It goes away, it cancels out. So, so these horizontal components cancel, and you only end up with one component this way. So we need to figure what that would be. So we figure out the direction of the magnetic field. It would be in the z direction. So I'm done with the cross product. So the magnetic field will be in the z direction. Oh, I should write dB here because it's a small field. It's only due to one segment. So dB, this one should have it back. So dB will just be in the z direction. We'll equal to this mu naught I over 4 pi. And then we need to figure out what this ds is. Okay. And I figured out the direction already. So ds cross r hat is in the z direction, is in this direction, so I'm done with that. Divided by r squared, I will figure out what r is, or what r squared is. And then I need the z component, this component. So if this angle here is, let's say if this angle here is theta, then this angle will be what? 90 minus theta. But this angle and this angle are 90 because this and this are perpendicular to one another. So therefore this angle is what?
Theta.
That's also theta, yes. So I mean, if this is 30 degrees, this has to be 60. But if this is 60, then this has to be 30. So if this is theta, therefore this one is also theta. So I need to multiply by sine theta to get the z component. So times the sine of theta. Okay? Just a few more steps and this one is done. So you get the following. Yeah, that's perfect. Here, dB, u naught times I over 4 pi. We will figure what ds is in a second. ds over r squared. What is r squared? What's the distance from here to here? Well, the radius is r, this is z, so r squared will be equal to z squared plus r squared, right? Z squared plus r squared, square root, that would be r. So r z squared plus r plus capital R squared squared. So little r squared would just be z squared plus r squared, like so, right? The square root goes away. The sine of theta. The sine of theta is the opposite over hypotenuse. The opposite is capital R, the hypotenuse is r, right? Little r. So you have the opposite, which is capital R, over the hypotenuse is little r, which is z squared plus r squared square root. Okay. This is to the power 1, this is to the power half. When you multiply them, you get to the power 1 1/2, or 3 halves, right? 3 over 2. So you get, and you get capital R here. So that's combining. You got mu naught I times capital R 4 pi, and then z squared plus r squared to the power 3 halves times ds. Okay? Now ds. We need to deal with ds. So what is ds? ds is the length of a current segment along the arc. ds is what? The length of a current segment along the arc. So let me draw my loop. Here is, let me redraw my loop, but on the plane of the board, so we can see what ds is. So here is the loop. I'm drawing it right now on the board. ds will look like this. So let me call this angle here. Let me call this angle here d phi. ds will be this. This is ds. This arc. This is capital R. So what's ds in terms of phi? R phi. R d phi. Right? R times d phi. So ds will be R times d phi. So ds will be R times d phi. Okay. So B, therefore the magnetic field will be, let's combine everything. We get mu naught times I times R times another R. R comes from this, right? R times R is R squared. R squared. Divided by 4 pi z squared plus R squared to the power 3 halves dp. Now, you're going around the loop. Phi changes from where to where? From 0 to 2 pi, yeah. 0 to 2 pi. Well, when you integrate it, you just got 2 pi. Get 2 pi. Well, there is a 4 pi here. So 2 pi over 4 pi is just, you would just have a 2 in the denominator, right? You have a half. So you will get mu naught I R squared over 2 z squared plus R squared to the power 3 halves. Okay, that's the result we're looking for. The direction along the z-axis. That's the direction. Now, people usually are interested what is the magnetic field at the center of the loop. Right? What's the magnetic field at the center of the loop? Well, if you want to figure that out, what do you let z equal to?
0.
0. Let z be 0. So at the center, z is equal to 0. Therefore, b, well, if z is 0, you will have r squared to the power 3 halves. What is r squared to the power 3 halves? R to the third. But you have an r squared on the top. So r squared over r to the third is what? 1 over R, yeah, so just an R. So it ends up being mu naught times I over 2R. That's what it simplifies to. Okay? And then, there's just one more. Okay? There's always one more, right? The one more is, what if you have the loops stacked on top of one another? A loop on top of a loop on top of a loop, like a coil. So you take loops and you just stack them. That's how you make a stronger field. Make loops stacked on one another. So one loop produces this. So what do 2 loops produce? Times 2. So if you have n loops, multiply by n. So for n loops, the magnetic field will be B equal to mu naught capital N times I over 2R. This is called the coil. We will do a solenoid later. A coil is just wrapped around itself and it doesn't have any thickness, it's not wide. A solenoid will look like this. The coil is wrapped and it winds up helical, like a helix. We're going to do that today. Alright? So this is for one loop. At what position? At z equal to what?
0.
0. This is for n loops at z equal to also 0. Alright? Now, off axis, on the axis of the loop, so here is the loop, the magnetic field will look, along the axis it looks like that. But off the axis, the magnetic field will start to look, if you're really close, it looks like this. If you're off the axis, it's something like this. Okay. You can look up a nicer picture in the book. And by the way, a current loop, you see now, you got the magnetic field starting here and then looping back. Looks like a bar magnet. Doesn't it? A bar magnet, you have a north, magnetic field starts north and comes down. And this is called actually a magnetic dipole. The current loop is called a magnetic dipole, which we might discuss it also today. Okay? So, here is a question. Let's just do a quick one. I will use this side of the board. So here is the question. Suppose you have suppose we have a 5-loop coil with current, actually with radius r equal to 5 centimeters. We want to produce a magnetic field B equal to 5 times 10 to the minus 5 Tesla at the center of the loop, or at the center of the coil. Center of the coil. So that's the magnetic field we want to produce. This is a small field. Does anybody know what this field, like there is a common magnetic field that's equal to this?
Is it the magnetic field of the Earth?
That's true, yes. So, yeah, magnetic field of the Earth. If you write this in another way, it's 0.5 times 10 to the minus 4. And 0.5, and 10 to the minus 4 Tesla is called the Gauss. So 0.5 Gauss. The magnetic field of the Earth is about 0.5 Yeah. Anyways, so let's say this is the magnetic field you want to produce. You're given the radius of the coil, how many loops you have, how many loops does your coil have? And the question is find the current. Find out. What current should you use to produce this? Well, that's a quick application of what we just derived. So we're going to write that. So solution, the magnetic field is at the center is mu naught times capital N times I divided by 2 times R. Therefore, the current is equal to 2V times R divided by mu naught times capital N, right? Now we plug in the numbers. It's plug in. So 2 times the magnetic field, 5 times 10 to the minus 5 times R. R is 5 centimeters, which is 10 to the minus 5 times 10 to the minus 2, right? Meters. Mu naught is, does anyone remember the value? 4 pi times
10 to the minus
right.
7.
Yeah. It's 4 pi times 10 to the minus 7. That's mu naught, and N is 5. The number of loops is 5. So this 5 can cancel. This 5, 10 to the minus 5 times 10 to the minus 2 is 10 to the minus 7, and that can cancel this 10 to the minus 7 on the bottom. Right? And so here you end up with 5 times 2, which is 10, 10 over 4 pi. 4 pi is almost 12, so it should be slightly less than 1. Right? 10 over 12 something. So less than 1, and according to the calculation here, it's about 0.8 times. So prime. 0.8. So the current is measured in what units? Amperes. So we gotta give credit to amperes. So we need to talk about Ampere's law now. That's the next. So we're going to talk about Ampere's law. Ampere's law is equivalent to Biot-Savart law, just like Gauss's law is equivalent to what's his name's law? Coulomb's law. Sorry, it's stuck from. But Gauss's law is more powerful than Coulomb's law when you have symmetry. Same thing here with Ampere's law is more powerful than directly computing magnetic fields using the Biot-Savart law. So that's what we're going to talk about. So the first one, we're going to use our result from the Biot-Savart law and then see what we can do with it. So consider a current that's coming towards us. Let's consider a current that's coming towards us. So here is the current, and it is coming towards us. Right here. So this represents current or magnetic field? Current, good. So don't confuse, the setup. So in this case, this circle with a dot is a current that's running this way towards you. Why do I draw it this way? Because it's easier to draw the magnetic field. Now, I want to do the following integral. Let's say I'm a distance r away. And I want to integrate counterclockwise like this. And here's the integral I would like to do. So b dot ds over a closed loop. That's the integral I want.
Surface integral?
Huh?
The surface integral?
A line integral.
Okay.
Yeah, so I'm integrating over a line. Yeah. So I'm integrating over. So how do I integrate? Let's call let's call the following, so before actually I proceed, is everybody, does everyone understand the setup of setup? So current coming out, and I want to do this mathematical problem. Integrate, take the dot product of b dot ds and go around the loop. And here's ds. ds is these segments that go around the loop. That's ds. I want to go around the loop. So first, ds, let's write down what ds is. ds will have a value, it's the arc length. And let's call this angle here phi. So that, or d phi actually, because it's a small angle, d phi. So we just did it earlier, was r times d phi, right? R times d phi. That's the magnitude of ds. In what direction is it? Well, it's around the loop. How do you name that direction when you go around? You give it a name. You have to give it some unit vector. Is it in the r hat direction? Is it away? No. It's in an angular direction, right? It's in an angular direction, and we call it phi hat. So it's in the direction phi hat. By phi hat we mean the angular direction. Okay, it's in the angular direction. Let's write down the magnetic field now. The magnetic field, well, this is a current carrying wire. The magnetic field due to a current carrying wire is mu naught times I over 2 pi r, right? That's the magnetic field due to a current carrying wire. In what direction is the magnetic field due to a current carrying wire? What does the magnetic field do around the wire? Goes circles around the wire. So it's in what direction? It's in the circular direction, right? In this angular direction, in the phi hat direction. So it's also in the phi hat direction. So we want to take, right, this integral says, find p, find ds, take their dot product, and then integrate around the loop. That's what we're going to do. So we found ds, we found p, let's dot them together. You got two vectors, and they are in the same direction, so what's the dot product of phi hat with phi hat? If they were perpendicular, it would be 0.
1.
It's phi hat, that it would be 1, because each of them is magnitude, is a unit vector, right? It's a unit vector. So when you dot a unit vector with itself, you always get 1. You just get the magnitude of the unit vector squared, but it's 1 anyways. So yeah, this dot product will result in the following. You will have phi hat dot phi hat is 1, and then you have an r on top, and then r on the bottom. What happens when you multiply r d phi, and then there's 1 over r here, that cancels. The r cancels. So we just end up with this. B dot ds is equal to mu naught times I over 2 pi d phi. That's what we end up with. Okay? So that dot product ends up with this. I'm trying to motivate this Ampere's law. Okay? So let's integrate now. So the integral says I want to do this over a closed circle. So I got mu naught I over 2 pi dt. Everything is constant except for phi. So we're going around the loop. So again, phi goes from 0 to 2 pi if you loop around once, from 0 to 2 pi. So this result would just be a 2 pi. But I have a 2 pi in the bottom. So what does this integral boil down to?
Mu naught I.
Just mu naught I. So it seems like when I do this integral, I just get mu naught times the current that goes through my loop. But this was a circular loop. What if the loop is not circular? Does it work the same way? The answer is yes, it does work the same way. Let's see why. So here is the same setup. This is going to be basically qualitative, but here's an arbitrary, more arbitrary loop. Here's the loop, and I will try to draw something like.
It's an avocado.
Huh?
It's an avocado.
Yeah, they're right, yeah. It wasn't intended, but. Okay, so that's my loop. I'm going counterclockwise. Okay, that's my loop, and it's supposed to be arbitrary, okay? Not a circle, it can be any shape. So, and I want to perform the same integral. So first, here's the integral one, b dot ds, all right? So first of all, the magnetic field still loops around the loop. The magnetic field is still in circular direction no matter where you are. So the magnetic field is still mu naught times I over 2 pi r phi hat. It's in that circular direction. That's the magnetic field. Now how about ds? Well, it depends where you are. So let's say, where's the spot? Let's say I'm here, at this spot. Okay? I'm at this spot. So let's draw ds. Here's ds. It's this red. That's ds. Notice ds will have two components. One component is in this direction, and another component is in this direction. So two components. And it's the sum of those two components. So ds will equal to this component that's tangent or in the circular direction will have length r dphi, and it's in the phi hat direction. So it's r dphi, and it's in the phi hat direction, just like this one. But it also has a component that's in the radial direction. So plus r, no, not r, dr r hat. Okay. This component that's this way is of size dr, and it's in the r hat direction. It's in the r hat direction. Now when you take the dot product, phi with phi hat, you get 1, right? They're dot product. You get 1 and you get exactly the same thing we had earlier. How about the dr and r hat? What's the dot product of phi hat and r hat? 0. It is 0, because they're perpendicular to one another. Phi hat is angular, r hat is radial, so they make a 90-degree angle with each other at all times. So you get 0. So their dot product is 0, and so b dot ds will again give me, so this dot product gives 0. This dot product gives exactly what we have here. So you got mu naught I over 2 pi dphi. So now plug this into the integral and integrate. Well, that's exactly the same integral. So you got mu naught times I. So let's write a more general statement. I mean, it would be exactly this statement, but I will add a little subscript. Because what if my loop, you see,